Here we have a circle. The area of the circle is pi times the square of the radius. And this equation right here shows that how the area and the radius, how they're related. And what we like to look at now is look at the rate of change of the area and look at the rate of change of the radius and see how they are also related. So here we have a circle, and if we increase the radius, we know that the area will also increases. And so if the radius increases at a certain rate, and then the area also increases at a certain rate. And so we like to know how the two rates are related. The rate of the change of radius and the rate of change of the area of the circle. And so we can see that if the rate of change of the radius is increasing faster and faster, then the area also increases faster and faster. And notice that the radius changes over time with respect to time, and the area also changes with respect to time. And so let the rate of change of the area with respect to time, we'll call it dA dt. So this is the change of area divided by the change in time. And so this is called the rate of change of the area. And this is the rate of change, this is the change in dr is the change in radius. And dt is the change in time. And so dr over dt, we call it the rate of change of the radius. And so we like to know how are these two rates, how are they related. Just like the area and the radius, they related by this equation. So we like to come up with an equation that relates the two rates. And so what we're going to do is we're going to do implicit differentiation. And so we want to do implicit differentiation with respect to time. And we want to do with respect to time because the area changes with respect to time, and the radius also changes with respect to time. And so here we have this equation right here, and we'll do implicit differentiation with respect to time. This equation is the same as 1a equal to pi r squared. And so we'll take the derivative of this term with respect to time. And so recall that here the variable is a, and we're doing derivative with respect to time, and so we have to use the chain rule right here. So the derivative 1a is just 1, and then since the variable is not t, then we have to use the chain rule and do times dA, the derivative of a with respect to time. And same thing over here, we're doing derivative with respect to time, which is t, and this variable is not t. And so we're going to have to use the chain rule, and then we'll get dr dt at the end. And recall that pi is a constant, and so it would be the constant, and then times the derivative 2r of r squared is just 2r. And then since r is not t, then we have to use the chain rule and multiply by dr dt. And this is the rate of change of the area, and this is the rate of change of the radius. And so this equation right here shows us how the two rates are related. And so normally we write this as 2 pi r. And so this equation right here shows how the rate of change of area and the rate of change of the radius are related. So just like this equation shows how the area and the radius are related, and this equation shows how the rate of change of the area and the rate of change of the radius, how they are related. They're related by this equation. And so as we're given that the rate of change of the radius with respect to time is 7 inches per minute. So radius is increasing at a rate of 7 inches per minute. And at the instance when the radius is 4 inches, we like to know what is the rate of change of the area at that instant. So let's look at the circle again. So as the radius changes, and so let's say that it starts right here and then it starts increasing. And so we like to know, and then at some point in time, at that instant, the radius is 4. And we like that at this instant, the area of the circle is 50.26. And so we're given that the rate of change of the radius is 7 inches per minute. We'd like to know at this instant, what is the rate of change of the area at that instant? How fast is the area changing at the instant when the radius is 4? So that's what we're looking for. So we'll use this equation right here to get the rate of change at the instant when r is 4. So we got 2 pi, and then times, and then at the instant when r is 4, and we are told that the rate of change of the radius is 7 inches per minute. So this becomes 56 pi. And then we multiply this out. This comes out to be about 175.93. And this is area, so it's going to be square inches per minute. And so at the instant when the radius is 4, the area is changing at a rate of 175.93 square inches per minute. So at the instant when the radius is 4 inches, the area is changing at a rate of this 175.93, so almost 176 square inches per minute.